challenges and opportunities. So some of you have been here since the morning. Some of you are just here for the evening session. Just a quick overview of what we've done so far. So this morning we had Peter Himes, Chief Strategy Officer of 4DS Memory, come and start the day. Then we had Kyle Hall from Ineotech. Then we had two really amazing researchers, Dr. Baochun Li and Dr. Gennady Pekimenko, do some presentations about some of their emerging research. Then we moved on to innovative startups and funding. So we had some entrepreneurs here, some of the companies that went through Zen Launchpad's incubator, as well as some others. And we were really happy to have Dr. Abhay Gadapande moderate the session. And we looked specifically at some of the companies in the AI sector, high performance computing. And then at 4:30, we had Professor Li, who's going to be speaking in just a minute. Dr. Dong Li, Associate Professor of Computer Science and Engineering, University of California, Merced, did a talk about learned tensor offloading, GPU memory, efficient execution paradigm for large deep learning models. And then finally, before we went to the dinner and the networking session, we had Guanhua Wang from Microsoft, and he talked about 0++, extremely efficient collective communications for giant model training. So it's been a really interesting day so far, and a lot of really awesome speakers, so we appreciate everyone who participated. Now this evening, we're continuing on the theme of innovative research, the future of heterogeneous computing, technical challenges and opportunities. And some of the main themes that we're looking into are peer-to-peer architecture and hierarchical memory, challenge of large-scale memory systems, innovations in memory management, network innovations for resource pooling, and challenges in hardware cache coherency design. So the format for this next part, and by the way, my name is Siri Jones with Zen Launchpad. We're really happy to be hosting this conference. And I wanted to say also a special thank you to all of our sponsors for this event. So our sponsors, sorry, I'm just scrolling this up here. We're 4DS Memory, CentML, Ineo, Sprout Fund, and Abhay, do you want to just wave your hand? He's still, so he's going to be actually on the panel tonight, and he was kind of wearing his venture capitalist hat tonight, giving some tips on that. Zen Cloud, and then we have silver sponsors, Hatrio AI. I think Dinakar, if you want to raise your hand, was one of the panelists earlier in the day. John D. Labs, I think Manjeet just had to leave. Logis Rich, Manood, are you? I'm not sure if he's still here. Nubel, Time and Space Technology, so Gabriel over here. And finally, Upsurge 3D. So we really appreciate these sponsors making today a really special event. We're also really honored to have Dr. Arvind Shriman as the moderator for the evening sessions. We're going to start by having 3 presentations, 1 face-to-face, 2 online, and then we'll have a moderated session. And appreciate his participation. I'll introduce him kind of more formally in a little bit, but for now, I'd like to call up Dr. Dong Li, Associate Professor of Computer Science and Engineering, University of California, Merced, and data centers in the heterogeneous computing era. So please give a round of applause for Dr. Dong Li.
Thank you. So the link is the talk. I sent you the link.
Oh, you sent the link? Okay.
Yeah.
Just one sec.
Thanks for the introduction. So in this very short talk, I'm going to introduce a system we are trying to build and commercializing. So yeah, we are running it into a business. So this system we are trying to build is a decentralized operating system for AI workloads, orchestration and scheduling at a global scale. The basic motivation behind this work is that the current AI model development is very expensive. It's only, you probably heard this story from many news channels, how expensive it is to train Llama 3, Gemini, and so on. And also, it's hard to find a facility with infrastructure and power at such a large scale. And nowadays, the AI development is mostly driven and controlled by private investment. So this kind of a thing creates a lot of barrier to make AI accessible by many people. And as a result, we couldn't push the AI adoptions in a largest scale. On the other hand, we see many opportunities in the crisis with AI centralization problem. Yes.
One quick change on here. Just be 1 second.
Right.
Excuse the interruption.
We're not getting your slide.
By the way, we have a live stream today as well, so there's people around the world watching the presentation, so we're just going to do a quick setting change. Oops. Slideshow? Yes.
Thank you.
Yes, thanks.
Thanks.
Yes, sorry for the interruption. So I will continue. At the very beginning, we mentioned this AI development problem, right? And that problem fundamentally comes from the fact that we are using a centralized system to run the AI model. We are using maybe one data center to run this AI model or train this AI model. You know, this decentralized system creates a lot of barriers for people to access AI models. And meanwhile, we found that there are many opportunities in the crisis of this such AI centralization. We found that many AI infrastructures is actually underutilized. Look at this figure. This figure shows the GPU utilization in a spectrum of GPU clusters. And no matter how large this GPU cluster is, the underutilization problem is quite common. So you see the problem. The hardware is underutilized. So this is a hardware provider perspective. If you look at the user perspective, you see that there's a strong demand for personalized AI. Ideally, you want each person to have one AI model, right? Working with you as a personal assistant. But a single user or individuals couldn't get access to such AI infrastructure to meet their needs. So you see there's a missing link between demand and provider. So this is our opportunity. And on the other hand, from the AI model perspective, we also see some opportunities. So this is a little bit technical oriented. If you look into AI model itself, you can see that the AI model can offer various level of parallelism. You probably heard about this story in the afternoon. We have pipeline parallelism, data parallelism, and so on. This parallelism itself allow you to decompose computation and map them into the underlying hardware to make best use of hardware. So this is an opportunity for us. And there are many solutions, actually. There are many solutions based on the Web3. And they offer a GPU marketplace. The basic idea is that I list those idle GPUs in my data center into the website. So you're probably familiar with this Craigslist, right? Craigslist. I don't know if Canada have this same commercial model or not. But they list GPU as hardware in a Craigslist. So people will get that GPU, you know, the website basically is like GPU marketplace. But the problem is that they trying to address the supply side problem. You can get hardware, but the demand side challenge remain largely unsolved. For example, if you want to train a very large model, but that large model cannot be accommodated in a single geological place. You only, let's say you only have 2 GPUs on your geological place, but your model needs 4 GPUs. What should you do? So this marketplace solution cannot solve your problem. And also, the user want to have a pay-as-you-go based solution. If I use hardware infrastructure to generate, let's say, 100 tokens, then I only want to pay money for that 100 tokens. I don't want to pay extra money, right? So this kind of functionality is not there yet. So our product mission is to empower AI innovation by orchestrating AI workloads and harnessing the global hardware at Utah scale. So what is Utah scale? Utah scale is about 1 million times of exascale. You probably know the exascale, right? Exascale is the largest supercomputer nowadays in the world. So by aggregating these computing resources at global scale, we are able to offer such AI infrastructure to the to the individuals, to make AI models accessible by many, many people. And this, our project is built upon a team of experts from industry and academia, and our work has been published, has been widely adopted by industry. I'm not going to go through this because of limitation, time limitation. But the major selling point in our project is that we offer extremely high performance, even at this geo-distributed scales. So you probably can imagine that in such scale, you have long latency across data regions, data centers. You have low interconnect bandwidth. How to handle those technical challenges to bring highest performance to end user is extremely challenging. And also, our techniques is allow the user to train AI models or deploy AI model inference on wide spectrum commodity GPUs with limited RAM. So that basically means you can use middle end or low end GPU to reach high performance, almost equivalent to high end GPU. So if you look at the whole ecosystem, the current AI whole ecosystem, you will see that we have model, data, application, agents, operating system, compute, and we actually position ourselves into the OS level. So this is kind of resource management and orchestration, and we are the only solution that can provide such solution in a geo-distributed setting. So as you can imagine, in our system, we have geo-distributed GPUs, and beyond that, we have some special nodes called the broker nodes. So broker nodes, so if you are familiar with Web3, you will know that the broker nodes allow the user can stake on the nodes and allow beating resources that matching computation requests to the most suitable hardware. So the idea is like Uber, right? In Uber, you can offer the customer this free, this idling driver resources to the user. And we are offering these idling GPU resources to the AI model users. So it's like Uber in nature. So a little bit technical, even the technical contents in these slides and next slides. So I'm trying to give you a high-level overview on what we are trying to build and why this software is so magical. So at the application level, we can provide a service for model training, inference, fine-tuning, and multi-engines. And underlying the hook, we have the parallelism management. As we mentioned at the beginning, we have different level of parallelism. We want to trigger those different level of parallelism based on the hardware availability. And we also automatically decompose computation into macro operators and fine-grained operators. And then we have a middle layer to schedule those operators with the functionality of fault tolerance, load balance across geo-distributed resources, and trigger the communication based on the highly optimized communication mechanism so that we can leverage those resources at planet scale. So these slides give you a little bit more techniques. So assuming that you are a client and you launch an AI model with many transformer blocks, and each transformer block, of course, has many computation demand, and then we are going to build a computation graph. In nature, this is an operator collection with dependency, and then we are going to reorganize those operators and then map them into underlying hardware. In this example, we have 8 sites. And different sites offer different computation capability. Some sites are very powerful, like site 1. But some sites is just a laptop. It's a very low-end GPU available. We are going to map the computation requirement into these computation resources. Meanwhile, we pay special attention to the communication overhead so that we can minimize we don't suffer from the long access latency. And the system will automatically decide what parallelism we should apply. For example, inside one, we have a powerful interconnect and a powerful GPU, so we should be able to automatically decide the model parallelism, apply model parallelism to this specific site. So we have some preliminary results to demo the powerful system. In this evaluation, we are trying to run a GPT-3 model with 1.3 billion parameters, and the metrics is floating point operation per second. So so the larger is better. And we use 4 geo-distributed AWS regions for evaluation. And in total, there are 64 via 100 GPU. And we evaluate system using a decentralized system. That basically means we use 4 regions. We compare our systems with Microsoft DeepSpeed, NVIDIA Magtron, and SSE. SSE is the state-of-the-art academia work published in Europe last year. So we have 2 groups of bars. If you look at the red group of bars, you will see that our system outperform DeepSpeed from Microsoft and Magtron from NVIDIA by 2.8 times and 1.6 times. This is because those 2 systems are not designed for decentralized system. They don't pay attention to the scheduling. They don't pay attention to communication performance optimization. As a result, their performance is much worse than us. And even compared with SRE, the state-of-the-art system, we are still 21% faster. In general, okay, I have one more slide. So I hope I don't run out of time. Behind the scene, we also use this Utah token. So this is a Web3 based idea. If you are familiar with Bitcoin, you will know what I'm talking about. So token is used as the incentive mechanism. So if you are AI model user, you can buy the system, buy the service using tokens. And then the GPU provider will provide the token. Will provide the service, provide hardware infrastructure, and get the token as a return. And the tokens is managed in the marketplace, and token price can go up and down. But in general, it can work as an incentivized mechanism and a penalization mechanism to engage users, to engage hardware providers into the community. Okay, so I probably will skip this slide because of a long presentation. But overall, I want to give you a takeaway message. So basically, we are trying to build a Uber for AI because we can match-make AI workloads with global infrastructure. And we use a decentralized technique to achieve the Utah scale with commodity GPU. And we unleash the power of community-driven AI development by using the tokenization mechanism. So that's it. Yes, thank you.
Okay, so we have some time for questions for Dr. Lee. Like you first. Yes. Ape.
Yeah, from the hardware provider perspective, what they need to do is register their GPU into the network. Maybe give the public IP information into the network, and then the software is in charge of scheduling and workload assignments, things like that. Yeah.
Is this network already online? Like, are there already nodes?
Sorry, what's your question?
Are there already nodes in the network?
How many nodes?
Are there nodes in the network right now, or is this?
Oh, how many nodes in the network? Sorry.
Yeah, so far.
Yeah. So far, we have about 100 GPU. We don't count nodes, we count GPU. How many GPUs are there? Yeah, sometimes one node can have multiple GPUs. So yeah, you got the idea.
And how can you leverage like these GPUs now if you wanted to, if you had some AI training implementation you wanted to use?
Yeah, so now as a user, you will have a notebook-like interface. So if you are working on AI model, you probably know what I'm talking about. The notebook is a programming environment, a development environment for AI model users to launch model, things like that. So if you are familiar with this, you can just launch a notebook and then you run your model. So this is like a service. You don't even know where your model is running. Okay. Yes.
So by building this system, who do you think most benefit from this kind of system, like customers, typical customers, from your opinion?
Yes. So our potential customers include the hardware provider and AI model practitioner, right? So from the hardware provider perspective, they can monetize their idle hardware, right? Now they don't waste their GPU cycles. And we have been trying to build up a partnership with the hardware providers such as IO.net, Lambda Labs. And from the AI model perspective, so we have a potential customer coming from the traditional manufacturer. So by traditional manufacturer, I mean there's petrol engineering, the material science, bioinformatics. And those customers are very like this kind of environment very much because they don't want to buy expensive AI infrastructure, and they don't want to use AWS because even for AWS is too expensive for them, and also AWS cannot provide a customized environment for them. For example, if you are working on material science, you probably have a special requirement on the data structure you want to use. So you want to have some customized solution, and AWS cannot offer such a unique solution for every single customers. Yes.
Okay. We still have time for a question. Okay. So a two-part question.
Yes,
First
please.
was just a, I guess a business-related question. So which public cloud is going to make their resource available to you for free? Meaning, how do you pay? So Amazon, let's say, has idle resources. Is Amazon going to sign up to Yota OS, and how do you pay Amazon the money? Like, you're making money, but how do they make the money is the question.
Yeah. So, actually this product is against Amazon because they are using a centralized system, and the centralized system has a limitation. Because it's too expensive, it cannot be accessible by many users. So we are trying to take that niche. So those customers just cannot be happy with AWS.
Okay, and then the second technical question is typically in training you have an all gather or a broadcast phase, right? So the slowest GPU kind of controls the performance. So in a distributed training phase, like let's say I have a laptop and a GPU, is the laptop speed now control the overall training speed?
Yeah, actually, that depends on this is a very complicated question. I have to say there's a lot of answers in my brain, but I will try to make it simple. In nature, we are trying to do the model and runtime co-design. So by co-design, I mean that when we do the training, we actually use two optimizers. One optimizer working on, so using this two-level optimizer allows us to reduce the communication significantly. And if your GPU is simply too low end to run these workloads, then we will just skip. So internally, we have performed the model to decide whether this GPU should be employed for this work. Yeah.
Thank you. I got two simple questions. First one is, what are the factors you will consider to schedule your task to different computing resources? And the second question is, from the user point of view, are they know where my task has been scheduled? Do I need to understand that we have a different computing resource underlying? Is that transparent to the customer, like a user?
Yeah, so first question is about what should be considered when we make the scheduling. So when we do the scheduling, we consider the memory capacity in your GPU and your GPU compute capability, basically flops per second. And we also consider the inter-GPU communication bandwidth. Yeah, so basically we have analytical model using those considering those factors to predict performance. And the second question is transparency to the user. So we have a world map. So if you log into our system, you will see the world map. The world map shows where the idle GPU is. So in that sense, our system is not transparent because the user can see, oh, there are idle GPU maybe in Vancouver and in Seattle. But when you really launch the workloads, you really don't know whether we are using Vancouver GPU or Seattle GPU. In that sense, it's also transparent to the user. User don't know where the work is run. Yeah.
Looks like lots of interest in this one. How do we invest in this company? No, just kidding. Okay, oh, question over here.
Thanks, Dr. Lee. It's a great talk. And so for my question is for what scale actually do you have achievement right now? And then if you for large scale clustering and should some modeling and some modeling to be used in your system and help to evaluate your and predict the scaling. So for because you have now is some workload is small, I think in the future will be more and more resource will be added in our system. So so the question here.
So
first one is what's the scale right now? You can.
What is scale?
Yeah, you can achievement.
What scale we can achieve?
Yeah, achieved. Yeah.
So up to now, the largest model we have been trying is about more than 100 billion parameters. That's the largest model we have been trying.
Mm-hmm.
Beyond that, we haven't tried. But I don't. So I don't want to say there's no technical challenge without any evaluation to support my conclusion. But for such large scale models, if we want to see whether its scalability is good or not, it really depends on your geo-distributed resources, where the resources are. And so I can give you a rule of thumb, very general conclusion. Of course, the answer will vary from one case to another case. But in general, if the interconnect bandwidth is like 1 GBS, 1 gigabyte bit per second, if like this, we can easily support more than 100 billion parameter training and inference without any problem. Of course, the larger bandwidth, better. The scalability will be better.
Yeah.
Yeah. I don't know whether it answers your question, but
okay.
Yeah.
So maybe some modeling and simulation for this thing?
Yes. Okay. As we mentioned, internally we have an analytical model to decide where the workload should be scheduled before the workload is ready to run. So we have some modeling effort. Yeah.
Thank you.
Yes, thank you.
Okay, I think we're going to have to wrap it up there to move to the next presentation. Thanks so much, Professor Lee. Very interesting presentation. So we're just going to need a couple of minutes to move to our kind of Zoom for the next presenter. So please just give us a couple of minutes. I will tell you who the next presenter is. We've got Dr. Peng Fai Su, Assistant Professor, HP CSA, Group Department of Computer Science and Engineering, also at the University of California, Merced. And he's going to be talking about memory wastage in data centers, pinpointing memory resource weightage in data centers via profiling. So that's the next up. We're just going to get it going here. Okay, welcome, Dr. Su.
Hi. How's it going? Shall we start or let's wait 1 more minute? Hmm? Can you hear me? The host. Yeah, interesting. Oh man. Can you hear me? I cannot see you guys. I'm being blocked. Can you hear me? Oh, man，哎，李老师，世嘉可以听到我呀？那你们现场听不到我，按说应该不是我这边问题吧？因为世嘉都是能听到我。李老师，那个世嘉能听到我的声音啊，所以应该不是我这边的问题吧？ Can you hear me? Yes, I know you can hear me. Oh yeah, yes, we can hear you. But oh, you can hear me right now? Ah, yeah, sure, sure. Yeah, I think so. So yeah, sure. Okay, sure, sure. Can you hear me? Can you hear me? Probably the. Yeah. How's it going right now? Huh? Yeah, well, I'm full also. Yeah. How about now? How about now? Is it clear enough or? Yeah, yeah. How's it? How's it? ？Hi there. Can you hear me? Yeah, yeah. Mm-hmm. Good afternoon, good evening, everyone. Can you, is it clear enough? Is that okay? Yeah. Yeah. 604. I'm not quite sure whether I can call it, I can make an international call. 604. Let me see. 604. Okay. 783 8601. 604 783. Yeah, I'm calling. Hi. Can you hear me? Hello? So we are going to use a phone to to communicate our.
You need a plan B here. Three things. They were trying to sort another reason. For some reason, the audio was not coming through. We tried to change different ways. We can try one other thing. Okay. Yeah, I'm going to hang up here. Thank you for trying something.
Mm.
So it doesn't echo. Another minute. That caused no trouble. Okay.
Oh, can you hear me?
Yeah.
Can you hear me? Can you hear me? How is the volume now? Yeah, how's it now? So it's oh yeah, then that's fine. So it's where okay finally okay we can start finally. So okay, hello everyone. This is Pengfei Su, assistant professor from UC Merced. So today it's my honor to be here and to talk about my research. And then in this short presentation talk, I will talk about how we pinpoint resource wastage in data center with performance profiling. So nowadays, as always, users always want their applications to run faster and consume less resources, no matter they are mobile applications, desktop applications, and large-scale parallel applications on supercomputers and data centers. So programs need to be efficient at all scales. Is everything fine? Is everything good? I heard some. Okay. Yeah, sure. So let me show you some examples about why performance is so important. So for Amazon, so every 100 milliseconds of latency can cost the 1% in sale, and for Google, every 500 milliseconds of latency in search engine can draw search traffic by 20%, and even worse for Meta. If a web page fails to load within 3 seconds, then roughly 40% of visitors will leave. So the classical profiling techniques typically they target hotspots that is high resource utilization, such as long execution time, high CPU utilization, and massive cache misses and frequent memory allocations. Definitely hotspot analysis is indispensable, but the hotspot analysis cannot pinpoint whether the resources are being used in a productive manner. So still a heavy burden is on the user to make a judgment call whether there is a scope to optimize a hotspot, even though they know this code snippet is a hotspot. So now there is a shift for tools from pinpointing resource utilization to resource wastage. And so in this talk, I will briefly talk about how we profile memory wastage on the CPU side and GPU side. Let's first talk about how we detect CPU memory wastage. So based on our case studies on many workloads, including data center workloads, we notice that memory wastage often shows up as three types of wasteful memory operations, like silent load, silent store, and dead store. So the first one, silent load, means your program repeatedly loads the same value from the same memory location, like this quite simple code segments. So we can see here that the array element AI is loaded twice from memory, while its value keeps unchanged in between. So clearly, the second store is unnecessary and can be bypassed by reusing the previous loaded value. And the silent load means your program repeatedly stores the same value to the same memory location. This is the opposite direction of silent load. So like this example, so here your program first loaded a value, an integer 10 to array AI, and then it loads the same value to AI again. So clearly, that second load is unnecessary and can be avoided by using the first one. And that store means your program stores a value to a memory location, while this value is overwritten without use, like this example. So it first stores a value to AI, and then immediately this array element gets updated. So as a result, the first store is overwritten by the second one without being used. So here, the first store and second store, they may have the same value or not. It doesn't matter. As the point there is that the first store is overwritten without having a chance to be accessed. So this is called dead store. So from these three examples, we can see that two operations get involved. One is silent or dead because of the killing one. So here, our solution to detect these wasteful memory operations is do binary level profiling. So here is a motivating example of why we do binary level profiling. Why not we take intermediate representation code or source code level representation profiling? So this example code is from spec CPU program. Now in this code, on my left-hand side is a code snippet. With a source code analysis, we can see that two memory stores associated with array element MCK, and the value of MCK is used in between, right? At line 3, right? The value of MCK is used. So from the source code level analysis, so there should be no dead stores because the value of MCK is used before the second store to MCK. However, if we do binary level analysis, for example, here, if we use like GCC or LLVM O3 optimization enabled, so O3 is the highest level of compiler optimization, then we will find that the result. Where's my cursor? Okay, the result computed at line 2 actually is first stored in the register R1 and then in memory location MCK, and also R1 register R1 is used for the computation at line 4. So there's a thing there is that if condition holds, then the second store to MCK would overwrite the first store to MCK. So as a result, the first store would be a dead store because it's never used before it's being overwritten. So the thing there is that the compiler, right? Our compiler like GCC, Intel, ICC, or many other commercial or open source compilers, they have no idea whether these three array elements MCK IP k minus 1 and TPIM k minus 1, they alias to the same memory location or not, because it's quite common that we can use different pointers in C and C++ to point to the same memory locations, but they have different names. So there's the thing there is that for the correctness, right? Correctness always comes first before performance from the compiler's perspective. So it should always guarantee that the program is correct. So then the compiler has to update the value of MCK at line 3 in case it's used in case IP k minus 1 or TPIM k minus 1 alias to MCK. So it has to update MCK in advance before it could be used at in the following computation. However, if we with further investigation, we are pretty sure that these three array elements they never alias to each other. So which means we can safely remove the first store without affecting the program's output, the result, the correctness. So here, the thing there is that you can see here, right? The takeaway point there is that the compiler sometimes may do harm than good, even with the highest level of optimization, code optimization, and also the high level source code analysis offers little or no visibility into the low level compiler introduced inefficiencies. So for the compiler introduced inefficiencies, a better way to detect is to binary level analysis. So for example, with binary analysis, we can see that the value of MCK is never used between the two stores to the same memory location. So this is the memory location of MCK. So clearly we can say that in between, right, between the first store to MCK and the second store to MCK, there's no instructions that access this memory location. So we can, it turns out that the first store is a dead store. It can be bypassed safely. So for example, a very simple code patch is that we can replace line 3 with an else branch to bypass this unnecessary memory store. So with this single line of code optimization, we can achieve up to 25% speed up on both GCC and LLVM clone compilers. So besides the compiler introduced inefficiencies, sometimes user inputs can also create significant memory waste. For example, in this code snippet is from Rodinia backprop or benchmark. So in this code snippet, we found that many silent loads associated with array delta at line 2. So the reason there is that most array elements in delta are zeros. So as a result, this program repeatedly loads the same value 0 from adjacent memory locations of array delta. And even worse, the computation associated with array delta is also unnecessary because any number times 0, right? If delta G is 0, any number times 0 equals 0, and any number plus 0 keeps unchanged, right? Which means we can, if we know delta array element delta G is 0, then we can bypass the computation associated with this array element. So based on the previous two examples and many other examples we have investigated, we found there are two basic types of silent loads and silent stores and dead stores. Temporal and the spatial silent loads or stores is kind of like the temporal and spatial data localities. So here, the temporal silent loads or stores mean your program repeatedly load or store the same value from or to the same memory locations, something like this. The program repeatedly loads the same value from the same memory location. While the spatial silent load or store means your program repeatedly loads or stores the same value from or to nearby memory locations. nearby memory location. So here, due to the time limit, I will skip the detail of how we detect these wasteful memory operations. But feel free to talk to me and offline if you are interested in this work. So next, let me spend a little bit time to talking about our recent progress in detecting memory wastage in GPUs. So the thing there is that there are several well-known problems regarding the GPU memory. So one thing there is that we know that the trend of developing deeper, larger, and wider neural networks requires significant GPU memory resources. So here I can show you an example. So for example, if a trillion parameter model with 3D parallelisms requires more than 300 NVIDIA A100 GPUs. But unfortunately, we know that GPU memory budget capacity grows way slower than the model size due to two hardware design trade-offs. One is that high bandwidth memory, HBM, must fit in a pretty small package space. And another thing there is that the GPU vendor, their highest priority is to increase is to reduce memory latency rather than increase memory capacity. So that's the hardware trade-off, design trade-off under the hood. So another issue there is that we find that the memory waste is prevalent in many deep learning models. So this is for example shown in this figure. So each pillar presents a model, a deep learning model like AlexNet, ResNet, BERT, and many others. And the blue segment represents the optimal memory peak of each deep learning model, and the red segment represents the actual memory, the memory waste related to each memory model, related to each deep learning model. So we can see here that the percentage of memory wastage is quite high, right? It's on average it's up to 80%. 80%. So this significantly affects the efficiency of how we use GPU memory effectively. So because the GPU memory capacity is already very restricted, but even worse, the memory wastage is prevalent in deep learning models. So our solution to mitigate GPU memory wastage is data object-centric GPU profiler. So this profiler consists of two components. One is object level analysis component. The other is intra-object analysis. So the object level analysis component, it focuses on memory accesses to data objects like arrays and deep learning tensors by treating the data object as a whole. And the intra-object analysis focuses on memory accesses to individual elements within an array or tensor. So this diagram shows the basic flow of our profiler. So our profiler works on GPU binaries. So it still performs binary level analysis to detect patterns of memory wastage. So here list the patterns of memory waste detected by our profiler. So including early allocation, deallocation, redundant allocation, unused allocation, over reallocation, and temporary idleness. So let me blindly use late deallocation and temporary idleness as examples to show how this profiler works. So suppose we have this code snippet, this CUDA code, okay? This CUDA code, it allocates three data objects in the GPU global memory, O1, O2, and O3, right? Three data objects, O1, O2, and O3. And our tool recalls the trace of GPU memory memory API invocations in the timeline. So here we have CUDA malloc, CUDA kernel launch, CUDA malloc, CUDA kernel launch, CUDA memory copy, CUDA memory set, as well as CUDA free. These 5 GPU memory APIs. So we use different shapes to represent them. For example, so here we use a rectangle to denote CUDA malloc, and star to denote CUDA kernel launch, and the circle to represent CUDA memory copy, and pentagon to represent CUDA memory set, and a triangle to represent CUDA free. We use timestamps to annotate when a GPU memory API is invoked. For like timestamp 0, for example, in this timeline, we can see here that the CUDA malloc is invoked at timestamp 0, and CUDA memory copy is invoked at timestamp 1. So then you can see here that the data object 01, so it's launched at it's created at timestamp 0 and copied and copied to GPU from the host to the device to the GPU at timestamp 1. However, it's now used during this time interval from timestamp 2 to 5, right? So which means it's temporarily idle between this time interval. So we call this type of memory waste temporary idleness. And for data object 2 and 3, we can see here that their last use happens at timestamp step 8. However, they are not released, they are not freed until at timestamp 11 and 12 respectively. So actually, for memory saving, right? We can release them immediately after their last use. For example, for object 02 and 03, we can probably use CUDA free to free them at timestamp 8, because their last point happens at timestamp 8. Okay, so this is what my talk includes. So thank you guys. So I know it's very late. So I'm happy to take any questions if any. Panel? Okay.
Grab a chair here, Dr. Lee. There won't be issues
Also,
here.
all the all the stuff is going through this laptop right now.
Yes. Yeah. Okay. So I'll just move both of you a little bit closer to this side, so you're a little closer to Arvin. So that way you can sort of.
Okay,
Yeah,
I can relay anything.
AI models to enable large AI model training and inference. And we found that actually the CXL memory is more than just providing large memory capacity. And we can also leverage its cache coherence nature to minimize the data movement overhead. So in particular, the cache coherence, how cache coherence take effect, right? Basically, this hardware mechanism allow you to track the data dirtiness, to make sure that we can have a global view on the data status. And now think about on CPU you have a data copy, on GPU you have a data copy, and then CPU and GPU are connected by CXL protocol, and there's cache coherence take effects. And if this cache coherence protocol is update-based protocol, not invalidation-based protocol, you can imagine that any data change, any cache line change, will be immediately propagated through the CXL connect and going down to the the main copy of that data. So that basically means Whenever you make any change to the cache line, the data transfer will be triggered. You don't need to wait for the completion of your change to be done. So that gives us a lot of opportunities to overlap computation and communication. So this afternoon we discussed a lot about tensor offloading, how to use CPU memory as extension to GPU memory to train large models. And in that context, the data movement play a very big role, play a very big overhead, right? And using this update-based cache coherence protocol in CXL, we actually can hide data movement overhead very effectively. So this is just one quick comment. I don't want to use too much time because Abe is probably waiting for further comment.
Does the other speaker have something to say? Is he going to also say?
Thanks, Ray. So the question is, do you have anything else to add? Did you hear the question? Did you hear?
No, I couldn't hear the question.
So the question, so there was Don was, or I asked Don was like, so what kind of workloads would kind of drive, the memory tiering, meaning what kind of workloads would predominantly use memory tiering? So do you want to add like a few words about profiling and the importance of profiling and how profiling like tiered systems might differ from non-tiered systems?
Oh yes, actually, Paul and I we have a paper regarding how we integrate profiling as part of the tools to profile shared memory. So at ATC, usually ATC 2024 this year. So yeah, definitely very different. So the thing that how can we collect useful information from profiling to guide memory movement from slow memory to fast memory and back. So yes, I would say that lots of applications and tools in this space, this area of how we
recording in progress.
To do a data migration in shared memory system.
Would you say that deep learning makes the problem easier? Because in the past, a lot of these workloads, you're writing languages that are not meant for it, right? But with deep learning, like with PyTorch and graphs declared upfront, is the profiling problem different? Or, okay, so let me say that, would it be fair to say it's easier? Is it different? Is it harder? Like, how would you characterize it?
I would say it depends, right? So if we are talking about GPU, if we are talking about GPU plus CPU memory profile, I would say the same complicates that one more. So because it's quite different in how we provide GPU applications compared to CPU applications. If we are only talking about CPU workloads, then I would say yes, it's easier in terms of deep learning. But if we are talking about heterogeneous computing, including CPU, GPU, and many other AI accelerators, then the thing really matters. So then the first of all, we need to coordinate how we use the unified profiling technique to coordinate, not make different compute nodes. Different types of accelerators like FPGA, GPU, and other stuff. And another thing there is that, so regarding deep learning, especially deep learning training, I would say it really cares about the profile overhead. Because the overhead, because training takes up to several days. So if the training overhead, if the profile overhead, if the profile introduce material overhead, then will be the problem.
Okay. Albert, do you want to say a few words from a business perspective as to
Really?
I guess the mic saying something.
No, I don't have any particular comments on this one. Oh, it's probably a No. I don't particularly have any comments on this one.
Okay, so next thing that I might segue into is, so Don is following up a little bit on your talk. So how do you see, so you're talking about wider distributed systems, right? So how do you see like tiling and things play a role within that aspect? That is it just another level? Is it like, so for example, like if you have NVIDIA's approach, right, the monolithic approach, so they talk about 450 gigabytes per second of bandwidth, NVLink, like, DGX parts, and you're going the opposite direction, right? You're trying to aggregate these resources from, like, so can you say a little bit about what the goal is? Because if the goal is it to beat NVIDIA's DGX parts, like, that's the market, right? Or is it something else? So how do you place what you're doing with respect to that?
Yes. My oh, there's some.
Yeah, that's definitely a great question and a fresh angle, right? So yes, actually yes, I haven't think about this question, quite quite. So but yes, I would say there's a lot of challenges and opportunities. Definitely in the distributed environment, the profiling. So one thing I can think of, I'm running in on my mind is that so in the distributed system, right? So we will collect lots of information, profiling traces. Then how can we extract useful information from those tons of profiling data? So that's one thing, right? So in case of we will the users will be overwhelmed by the profiling data. Another thing is that um actually there I know with the advance of like the agent, LLM agent, right? So actually, right now, a new way is that we can actually leverage the capability of LLM model agents to help users to analyze and extract useful information from the profiling data and also help the users to make the decision or optimization decision or suggestions. And another thing there is that how can we in the distributed system, like you said, right? How can we automate the process of the based on automate the optimization based on the data, the real time data collected from from different nodes. That's another interesting topic, but it's I would say it's quite challenging because probably we would like to do some online optimization instead of we do the optimization offline. Then we 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 patch we update we submit the patch to the running um running system. That I would say that's practically impossible, infeasible to do this. Mm. Yeah, yeah, I definitely I agree with Dong. Yes, that's true. There are many factors regarding this issue, right? Regarding the low utilization. So, but I can probably provide some insights from the programming side. So I actually we did some experiments to investigate models. Some models like PyTorch benchmarks. So we do see that there are several reasons. One is the memory bound. That's a reason. Restricted memory capacity. Another reason is that we do see that in some models we see a lot of tiny kernel launches, and the kernel launches the tiny kernel launches. So and the time the idleness between those tiny kernel launches can contribute to the low GPU utilization. Another thing there is that we use the like the roofline model to see the gap between the upper bound theoretical upper bound of GPU utilization and the actual achieved GPU utilization. We see the existing models, they do not well mitigate this gap. So because of the problem programming issues. So yeah, yes, and also there are many other reasons. Many other reasons like the compiler reasons. For example, the compiler does not do a good job of kernel fusions or also kind of compiler optimizations, or traditional optimize like loop interchange or loop or tiling, those kind of things, or like and as well as a memory inefficient memory access patterns like and many other like the memory stores, execution dependencies and low parallelism. Many reasons. Yeah, yeah, from the programming perspective. Yeah, that's a great question. Yeah, that's something I also want NVIDIA can improve the profiling for the fundamental profiling support as soon as possible. And so yeah, yes, right now the thing there is that I would say that the from the hardware side, right, the GPU hardware doesn't expose enough hardware facilities to help us to help the two developers to get more insight performance metrics and with lower overhead. That's one issue. So as compared to the CPU side profiling, the GPU side profiling is way harder to deal with. So and also from the software perspective, I hope the software interface can be easier to use. So that's another thing, and also provides more solid, I would say, more solid profiling interfaces for users. But because it's not uncommon that like the NVIDIA, right? NVIDIA sometimes it's still buggy, I would say. So we still can see some unreasonable, unexplained bugs. So and then initially we thought probably the reason the bug is from our own code, but actually turns out that it's actually from the NVIDIA provided instrumentation or profiling framework. So it's not as mature as Intel as a CPU side profiling frameworks. Yeah.